This is Mr. Beck Does Your Homework. This is homework number 8 about angled projectiles, launched at an angle, questions 4 and 5. I do give you a hint here. It says, Mr. Beck says, it is easier if you solve question 8 before question 7. I think I meant question 5 before you solve question 4, so ignore that 8 and 7 and make that a 5 and a 4. So if I solve this part, it might be easier to find the range if I already know the time. So let's see what this says. A shell is fired from the ground with an initial speed of 1.7 times 10 to the third meters per second, approximately 5 times the speed of sound, at an initial angle of 42 degrees horizontal. So I have this launch of 1.7 times 10 to the third meters per second, and it's launched at an angle of 42 degrees. The acceleration of gravity is 9.81. Find the shell's horizontal range. Well, in order to get the range, first let's worry about x world and y world. So I'm going to write x world, and I'm going to write y world and see what I know. In the x world, I know very little. I don't know the time. I don't know the distance. That's kind of what I'm looking for here. So already I know is that x equals question mark. I do know my acceleration is 0. In the y world, I know that my acceleration is negative 9.81 meters per second squared. Also in the y world, that's about it. I don't know much else. Oh, at the shell's horizontal range, when this shell comes up and it takes its parabola and it lands again, one thing I know is that the y is going to be back to where it started again. I'm going to go up and come back down. So I know that my displacement is going to be 0. Now, where does this 1.7 times 10 to the third fit in? In order to figure out something to do with that, I know that that is going to have an x component of velocity and a y component of velocity. So I know that my x component of velocity is going to be my overall velocity times the cosine of the angle. So if this is theta, because this is adjacent and this v is my hypotenuse, this velocity is my hypotenuse, that's my total velocity. So I can write v total cosine theta. And I know that my velocity in the y direction initially will be whatever this launches at. That's going to be my total velocity times the sine of theta. So I can plug these in up here. In the x world, I'm going to get this velocity. So this one goes right here in the x world. And then in the y world, this is my v0 is going to be my total velocity times the sine of theta. So now I've got an acceleration and a displacement, an initial velocity. I'm looking for my displacement here. I need a velocity and a time to figure that out. Well, there's my velocity, but I don't have time. So why don't I answer part B, how long is the shell in motion? Well, I've got a displacement, an acceleration, an initial velocity, and I'm looking for a time. I do have an equation that tells me that my displacement is my initial velocity times time plus 1/2 my acceleration times time squared. Now, you might say, wait, if you're going to solve for time in this, you are going to get a quadratic and it's going to be a mess. But wait a second, if I know that my displacement is 0, that's going to help me out. So if I have 0 is my initial velocity times time plus 1/2 my acceleration times time squared. If I subtract this from both sides, I'm going to get negative 1/2 gt squared equals v0t. Now you'll notice there's a t over here and a t squared there. So if I divide both sides by t, what happens is this one goes away and this is left at just t. So I get 1/2 gt equals v0. Sorry, that's a negative. Now if I want to solve for time, I can multiply by 2. I can divide by g. So I get my time. I'm going to run off the page there. I get my time, so if I finish this up here, I get my time equals v0 times 2 divided by g. And that's a negative, but that's going to be a negative, so that will give me a positive amount of time. So that will be the answer to question number 5, is how long is the shell in motion? So it's going to be -2, the initial velocity, divided by gravity. And remember, the initial velocity is my total velocity times the sine of, in my case, 42 degrees. Once I know the time, now I can go back and find the shell's horizontal range. Now that becomes an easy problem because the shell's horizontal range is just my x. So here in the x world, I know that that is going to be my velocity in the x world times my time. Since I know my time, I'm good here, where my displacement will be my velocity in the x world, which is my total velocity, this 1.7 times 10 to the third, times the sine of theta, sine of 42, that times my time that I just figured out over here. So this will give you your horizontal range.